Hey everybody, welcome back. So, in this video, I wanted to give you an idea of where differential equations come from. This whole list that I gave you in the previous video looks like I just pulled these out of my butt, right? I have no basis for where this came from, or I didn't explain it, or I told you where this harmonic oscillator equation would come from, but I didn't explain it with any rigorous detail, and I want to be able to do that in this video. So in that set of examples, these are by and large what we call mathematical models. And not all mathematical models have to be difference equations or differential equations, but differential equations are a really great starting point for building a model in the first place, something that has the ability, that has predictive capability. And I want to show you how that's the case. So let me give you just a generic idea of what's happening here. So let's say I have an object, and I can probably make that a little bit bigger. Let's say I have some object with mass m falling through the air. Now, typically what we say in physics is that, or what we do in physics is we create a free body diagram for this guy. And usually this is just given as mg times the k hat vector. So the idea behind this is that we're just trying to collect all of the forces that are acting on this object. Now, when we do that in this scenario, we are going to invoke Newton's second law. Newton's second law. There it is. And the idea behind Newton's second law is that mass times acceleration is going to be the net sum of forces, or mass times acceleration will be equal to the net sum of the forces acting on this object. Now, there are a lot of different ways to represent this equation, but when we throw this into the language of differential equations, we can actually talk about this in the following way, where I recognize that acceleration is actually the derivative of the time derivative of velocity. Now, why would I want to do that? I'll explain that in a moment when we change this problem ever so slightly. But Newton's second law would then become mass times dv dt is equal to, well, negative mg. And notice I've dropped the vector notation because everything is occurring in one direction. All the motion is occurring in one direction. So really this is just a matter of how do you scale vectors along a line. So I don't have to distinguish that things are happening in different directions. So if I say that velocity is pointing up in this direction, and we'll say whatever, this might be 0, the origin down here, that would be a coordinate system that I could lay onto this system to create this differential equation. But remember, the mass of the object and the gravitational acceleration are both constants when we're looking near the surface of the Earth, right? Little g doesn't change by a whole lot, so we just go ahead and ignore the tiny little change as this object falls. So what we actually have here is m dv dt equals a constant, and that's the same thing. So let me go ahead and just say dv dt is equal to minus g, and this is a constant on the right-hand side, which would mean that v of t, I can integrate this guy and get a constant minus g times t, right? And this would be, this c here is what happens if I plug in t equals 0. Which we're just going to go ahead and say here that the general notation for an initial condition is going to be this sub-zero or not notation. So usually we'll see this written v of t equals v naught minus g times t. And that is what would happen if this object were falling through the air with 0 resistance. And in fact, you could actually think of this as an object falling, like a small object falling towards the Earth in space, and there would be no resistance from any sort of drag forces. So this would be actually a really strong model if if that little g doesn't change too much. But we know that we have to account for that when the object is traveling over a long enough distance. But anyway, the point is that I can go ahead and create from a physical law an equation that relates the derivative of some function to another expression. And that would be, again, based off of some physical law. So the question now is, if this was so easy, I mean, let's change this up a little bit. I'm going to say that we're going to add a force to this guy. And that is a really hard color to see, so I'm going to do this in yellow. Oh, it's in pencil. That's why it's not coming up. So we'll do this in blue. That's showing up a lot better. There we go. Let's say that there was air resistance, and I'm going to call this guy a drag force. That would change what my mathematical model is as this object is falling through the air. And this is going to be reflected in Newton's second law equation. There's another force in here that I would have to take into consideration. So if I kill this off real quick, let me erase. Get out of here. Out of the way. Yeah, there we go. That means that this equation has to change a little bit. There's not just one force acting on this, but I would also have some drag force that's acting against the motion of the object. And again, this is going to be something where we have to kind of use empirical observations or intuition to tell us what this term should look like. Now, the whole reason why I'm using a derivative notation, or I'm using a derivative here, is because I want to use as few variables in this model as possible. Right? I could have just written this as MA equals minus MG plus FD, and then we look at that and say, yay, we have an equation, but okay, what do we do with it? That's kind of what we're doing here. We're trying to find a way to make this as simple as possible for us to study. And when we add this drag term, we need to not only add the drag term, we need to kind of say how this guy relates to other terms in the equation. And a simple pair of models that we could use here, FD could be proportional to how fast we're going, so proportional to velocity. There's also another model that says this guy could be proportional to the velocity squared at high speeds. But for right now, we're going to go ahead and use linear drag, just to illustrate the point. And the idea is that we have to create what's called a constitutive equation. Constitutive. Let me know in the comments how you pronounce that. Constitutive equation for this drag. And it's going to relate this force to variables that we already have in the problem. And we think about how a drag force would actually affect this system. And we think, okay, if I'm not moving, then I'm not going to have any drag associated with me, right? Nothing is going to be moving against me if I'm not moving against it. But the drag force will also be resistant to the direction where I'm moving. So if I have a non-zero velocity, then this force will be opposing that direction, which means that I'm going to have to be minus gamma v, where gamma is a positive constant, and this will be called a drag coefficient. Right? And this is just telling us that the drag force involved is going to be opposing motion, so negative v, and it's going to be proportional to that. And that's what gamma is doing. It's giving me this fudge factor in case I don't get the number exactly right. But this constitutive equation gives me a way to move forward in the problem. I make an assumption to be able to proceed. Minus, what would that be? Minus, yeah, oh shoot, there we go, minus gamma v. And I now have a new differential equation telling me how this block, this mass m, wants to move through the air when it has when it has drag associated with it. So the equation does not come out of nowhere. There is method to where this comes from, and what we would like to be able to do with our mathematical models, our goal here would be to solve for the functions v equals v of t, whose derivative dv dt satisfies this equation. Okay, and this is where we're going to go basically for the rest of this lecture series. We are learning some fundamental solution techniques for a very, very specific set of differential equations. And we'll talk more about why we're looking only at this particular cross-section of differential equations as we come across them in the series here. But the point is that we want to figure out which functions. So just like in any old algebraic equation, we want to figure out which numbers satisfy a certain equation. Well, in this case, we want to figure out which functions, right? The function now is the unknown, and we want to figure out